Declassified. For a decade, the most important manufacturing technology in the semiconductor industry, the physics, the engineering principles, the core architecture of extreme ultraviolet lithography, was locked inside American national security frameworks while the rest of the world's engineers worked in the dark. That was the strategy. Keep the knowledge scarce. Keep the ceiling out of reach. Last week, a research institute in China published what appears to be a functional EUV light source design. Open literature, peer-reviewed, available to anyone with an internet connection. I've been sitting with that for a few days now, and I still don't know exactly how to feel about it, which usually means something real is happening. Here's what makes this uncomfortable to explain. EUV isn't just hard. It's a category of hard that broke companies, consumed decades, and nearly bankrupted ASML twice before the machine worked. The light source alone, a plasma generated by firing 50,000 laser pulses per second at tin droplets the width of a human hair, took Cymer, an American company, over 15 years to make reliable enough for production. TSMC spent billions qualifying a single generation of EUV tools before printing one commercial chip. This is not technology that leaks easily. It doesn't travel through espionage alone. It has to be built, failed, rebuilt, and failed again. So when China's Changchun Institute of Optics, Fine Mechanics, and Physics drops a paper describing a laser-produced plasma EUV source with measured output in the 13.5 nanometer wavelength band, the exact wavelength the entire industry runs on, the correct response is not to dismiss it. The correct response is to ask how far back this work actually started and whether the classification strategy that was supposed to prevent exactly this moment may have, in some indirect way, helped accelerate it. That's the question this video is actually about. Not whether China has matched ASML, they haven't, and anyone claiming otherwise hasn't read the paper carefully. The gap between a functional light source in a laboratory and a production-grade EUV scanner capable of printing 3-nanometer logic chips is roughly the distance between striking a match and running a gas turbine. The engineering between those 2 points is monstrous. But the classification strategy was never just about the final machine. It was about keeping the underlying physics, the plasma dynamics, the debris mitigation approaches, the collector mirror geometries, out of reach long enough that the gap would stay permanent. That window may have just closed, not slammed shut, but closed. The U.S. Department of Energy placed EUV-related research under classification frameworks beginning in the early 2010s. Following work at Sandia National Laboratories and Lawrence Livermore that touched directly on laser plasma physics relevant to both weapons programs and lithography light sources. The dual-use problem was real. The logic was defensible. What nobody fully stress-tested was the second-order effect. When you classify foundational science, you also remove the competitive publication pressure that drives refinement. ASML's engineers in Veldhoven couldn't read what Sandia knew. Neither could the researchers in Changchun, but they could read each other, build on Soviet-era plasma physics literature that was never classified, and run their own decade-long failure cycles without anyone watching. America protected the ceiling. China studied the floor. And floors, if you dig long enough, eventually connect to the same building. Let me tell you about a specific number that didn't make headlines when it should have. In 2021, China's National Natural Science Foundation allocated 1.3 billion yuan, roughly $180 million, specifically to extreme ultraviolet light source fundamentals, not chip manufacturing, not fab equipment, the light source, the physics layer beneath the engineering layer beneath the commercial layer. They were funding the basement while Western analysts were watching SMIC's roofline. That funding decision didn't appear in semiconductor trade coverage. It appeared in a budget appendix, in Chinese, which is where a lot of the important decisions live. The Changchun Institute isn't a new player assembled in response to sanctions. It was founded in 1952, has roughly 3,400 researchers, and has been China's primary center for precision optics and laser physics for 7 decades. When sanctions cut off access to ASML machines after 2019, first the most advanced DUV systems, then any realistic pathway to EUV, Changchun wasn't starting from scratch. It was accelerating work that had been running quietly for years. Now, with urgent national mandate and essentially uncapped funding, the paper published last week came out of that environment. And the detail that keeps pulling my attention isn't the output power. Though 20 watts at 13.5 nanometers in band is not nothing, it's the debris mitigation approach they described. Tin droplet debris is the unglamorous problem that almost nobody outside the industry talks about, and it's one of the reasons EUV took so long to commercialize. When your laser vaporizes a tin droplet to generate plasma, the unvaporized tin fragments travel outward at high velocity and coat your collector mirror, which is the most expensive and sensitive optical component in the entire system. ASML's solution involved a combination of hydrogen gas flushing, magnetic fields, and collector mirror geometries refined over roughly a decade of production experience. It was not published, it was not patented in ways that revealed the mechanism. It was learned. The Changchun paper describes a foil trap geometry combined with a buffer gas approach that is, and this is where I want to be precise rather than dramatic, functionally convergent with approaches that were independently theorized in European and Japanese open literature between 2008 and 2015. They didn't steal the solution. They arrived at a similar solution via a different path, which is actually the more significant finding. It suggests the underlying physics constrain you towards certain answers regardless of where you start. That's how breakthroughs work when classification removes the shortcut. You can't copy the answer, so you rederive it. And sometimes, rederiving it makes you understand it better than the people who found it first. I want to be honest about the limits of what I can claim here. The paper has been public for days. Independent verification of their output measurements hasn't happened yet. Photon flux at the intermediate focus, the number that actually matters for exposure dose in a scanner, wasn't fully disclosed. There are questions, real ones. But here's what the classification framework was specifically designed to prevent. A Chinese institution publishing credible, peer-reviewed EUV source physics in open literature, establishing prior art, and signaling to every optics researcher in the country that this problem is solvable domestically. The psychological function of that signal is not measurable in watts or nanometers. It's measurable in the number of PhD students who now choose this problem over a different one. America classified the research partly to deny China that signal. The signal just arrived anyway, self-generated. Washington released updated export control guidance on semiconductor equipment in October 2023, a 139-page document that mentioned EUV 47 times. China's response, across the following 14 months, included 3 new EUV-adjacent research papers, 2 facility expansions at state optics institutes, and last week's announcement. The controls aren't failing because they're poorly designed. They're running into a problem the designers underweighted. You can restrict the hardware, but you cannot restrict the understanding that hardware represents once a determined institution decides to reconstruct that understanding from first principles. That's not an argument against export controls. It's an argument for being clear-eyed about what they can and cannot buy you, and for how long. Now I want to complicate my own argument. Because the version of this story where China is 6 months from printing 3-nanometer chips on domestically built EUV scanners is not the story the evidence actually tells. And if I let the momentum of the last 2 parts carry me past that, I'm doing the same thing I criticize in other coverage. The light source is roughly 15% of an EUV scanner. Maybe less. The collector mirror system, the illuminator optics, the reticle stage, the wafer stage, that last one moves a silicon wafer with nanometer-level positional accuracy at speeds that would embarrass a Formula One pit crew. The metrology systems, the photoresist chemistry, the computational lithography software stack. All of it has to work simultaneously, in vacuum, at production yield rates above 90% for a machine that costs $380 million and needs to expose hundreds of wafers per day to justify its existence on a fab floor. ASML has 40,000 employees. Approximately 5,000 of them work on a single EUV program. The company sources components from over 800 suppliers across 11 countries. Carl Zeiss SMT in Oberkochen, Germany makes the projection optics. Mirrors polished to surface tolerances measured in fractions of a hydrogen atom's diameter. There is no domestic Chinese substitute for those mirrors. There is no near-term pathway to one that serious optical engineers will defend with a straight face. So the gap is real. It's wide. Measured in years, probably a decade or more for production-grade EUV at advanced nodes. But, and this is the reversal I've been building toward, the gap is not the point. The point is what happens at the layer below production-grade EUV. The layer that most Western semiconductor analysis completely ignores because it doesn't map onto the TSMC versus SMIC competitive framing everyone defaults to. China currently manufactures the overwhelming majority of mature node chips, 28 nanometers, 40 nanometers, 65 nanometers process geometries that go into automobiles, industrial controllers, military electronics, power management systems, and the vast infrastructure of devices that don't need a 3-nanometer logic chip, but absolutely need a reliable domestic supply of something. Sanctions and export controls were designed with leading-edge logic in mind. They were not designed with the full picture of where chip dependency actually bites. Here's the number I want you to sit with. In 2023, China produced approximately 29% of global mature node semiconductor output. That share has grown in each of the last 4 years, entirely on DUV equipment, the generation before EUV, which China can now manufacture domestically in limited but expanding quantities through SMEE, the Shanghai Microelectronics Equipment Group, whose SSA 600/20 stepper reaches 28 nanometer production capability. The EUV story, the one everyone is watching, is a distraction from a quieter consolidation happening at nodes nobody films press conferences about. What Changchun published last week matters less as a production milestone and more as a proof of institutional capability. The message isn't, we can build EUV scanners. The message is, we have the physics talent, the funding continuity, and the organizational patience to reconstruct classified knowledge from first principles, and we're comfortable telling you that openly. That last part, the openness, is the part I find genuinely strange, and I mean that in a technically precise way. Classification creates asymmetric information. China's decision to publish rather than protect suggests either they've calculated the technology isn't mature enough to be worth classifying, or they've decided the signaling value of publication outweighs the intelligence value of secrecy, or, and this is the possibility I keep returning to, they're further along on something they're not publishing, and this paper is the visible layer of an iceberg being shown deliberately. I don't know which of those is true. Anyone who tells you they're certain is working from assumption, not evidence. What I do know is that the classification strategy America ran for a decade was built on a specific theory, that the knowledge barrier was high enough and the institutional capacity gap wide enough that restriction alone could maintain permanent technological distance. That theory had a shelf life. Last week, we got one data point suggesting the shelf life is expiring. Not expired, but expiring. The difference matters enormously. Expiring means there's still time to rethink the strategy. Expired means you're managing decline. Which one this actually is depends almost entirely on what happens in the next 5 years in 3 places: the optics labs in Oberkochen, the fab floors in Arizona, and the research institutes in Changchun that nobody was watching closely enough for long enough, until now. Pull back to the opening for a second. America classified EUV research to protect a ceiling. The assumption underneath that decision was that ceilings, once hidden, stay out of reach. It's a reasonable assumption if the person trying to reach the ceiling has no ladder and no lumber. It becomes a different kind of assumption when they've been quietly building both for a decade, in a language most Western analysts don't read fluently, funded by a state that treats technological sovereignty the way other states treat territorial integrity. The lumber was the 2021 NSFC funding allocation. The latter was Changchun's 70 years of precision optics infrastructure. The publication last week was someone standing on the top rung and taking a photograph. Not of the ceiling, of how close they've gotten. Here's my actual opinion, stated plainly. The export control framework the United States built between 2019 and 2023 was necessary, defensible, and probably bought 3 to 5 years of meaningful distance at the leading edge. I think it was the right call given what policymakers knew at the time. I also think it was designed to solve a 2019 problem and is now running on 2019 assumptions in a 2026 environment that has shifted in ways the framework hasn't fully absorbed. The specific assumption that needs revisiting is this: that restricting hardware automatically restricts understanding. It doesn't. It restricts the speed of understanding. Those are different problems requiring different responses. What would a 2026 calibrated response look like? Probably something uncomfortable for both sides of the usual policy debate. More aggressive talent retention, not just visa policy, but the kind of compensation and research freedom that makes a physicist choose Livermore over Changchun as a career decision, not a patriotism decision. Faster declassification of foundational science that China has now independently reconstructed anyway, so American researchers can build on it openly and recapture publication momentum. And a serious recalibration of where the actual vulnerability sits, which, as I argued in Part 3, is less about 3-nanometer logic and more about the mature node supply chain that quietly runs most of the physical world. My doubt, stated honestly, I don't know how much of the Changchun paper represents genuine independent derivation versus benefiting from knowledge that moved through channels that aren't visible in citations. The history of technology transfer is full of convergent-looking discoveries that weren't entirely convergent. I'm not asserting that here. I'm acknowledging I can't rule it out, and neither can you. My prediction, and I'll be specific enough to be wrong, within 36 months, a second Chinese institution, my guess is the Shanghai Institute of Optics and Fine Mechanics, not Changchun, publishes collector mirror performance data that moves the conversation from light source physics to integrated source optics system capability. That's the next technical milestone, and it's the one that would genuinely narrow the distance between laboratory demonstration and something a fab engineer has to take seriously. If that paper doesn't appear by late 2027, the current gap probably holds through the decade. If it does, the timeline compresses in ways that current export control architecture wasn't designed to handle. Watch the optics papers, not the chip output numbers, not the fab capacity announcements. The optics papers, that's where this story actually lives. The classification held the ceiling in place for 10 years. It bought time, generated distance, and probably delayed a capability that now appears to be arriving anyway. Just reconstructed from the floor up, by people who had no choice but to understand it more deeply than they would have if they'd simply been handed the answer. There's something almost instructive about that, not comforting, instructive. The irony is precise enough to be painful. The secrecy that was supposed to make this impossible may have produced engineers who understand it better than the people who classified it. If you've made it this far and you're thinking about this differently than you were 14 minutes ago, that's the only metric that matters to me. Share it with someone who thinks semiconductor policy is boring. It isn't. It's just usually explained badly.